morning, everyone. Happy New Year to online and offline participants. It's nice that so many people showed up here despite the nice weather outside. It's the first seminar for this year, right? First TRR seminar. And we are very pleased to welcome Ian Grooms, coming all the way from Boulder, Colorado. So Ian is a professor at the Applied Mathematics Department in the University of Colorado, and at the same time, he's a co-chair of the CESM Ocean Modeling Group in NCAR, just the National Center for Atmospheric Research in Boulder. And before that, he was with a postdoc at New York University, and before that, PhD in Colorado, so full circle. And today we are going to hear something very interesting about backscatter schemes, right? In the ocean. So just get started. I'm looking forward to your seminar.
Thank you very much, Manita, for the introduction. Thank you also, Karsten, for the invitation, Manita. And thank you all for coming on a day when there's unusual snow. It's actually very beautiful. Last time I was in Hamburg in January, it was just dark and rainy. And so this is, for me, a nice break. So I'm going to talk today about backscatter and ocean models. And the work that I'm going to talk about is, this is the usual thing. Pardon me, technical difficulties. There we go. It's the usual thing. So the work I'm going to talk about today was done as part of the NOAA NSF funded climate process team on ocean transport and eddy energy, which just wrapped up in the summer of 2025, a 5-year project with a short no-cost extension. Lots of people were involved in this project, too many for me to mention them individually. But I am grateful for their support and collaboration and glad to have been part of that project. I'm going to talk today about ocean models that are not high resolution. And I understand that a lot of people really like high resolution ocean models, and I think they're great. Some people, I think, would argue that there's no point in doing anything else because of the problems associated with lower resolution models. And I sympathize with that perspective, but high resolution eddying ocean models are also very expensive, and not every center can afford to run them. So the National Center for Atmospheric Research in the US is in my backyard in Boulder, Colorado, and I work closely with them on CESM, Community Earth System Model. And they do a lot of things, including climate projections from 1850 to 2100 and farther, long climate pre-industrial control simulations, several hundred years, ensembles, CESM large ensemble, Earth system modeling involving not just the physical components of the climate system, but chemical and biological components as well. These are all very expensive, and they're very expensive for very high resolution models. And so CESM at least still uses lower resolutions for a variety of purposes. And since they're still being used at these lower resolutions, I think it's still worthwhile to work on making those models better, which is what this research is about. So I'm going to start with eddy permitting resolutions. And the sort of canonical eddy permitting resolution is 1/4 degree, although it's sort of plus or minus. And these models have mesoscale eddies. The eddies that are permitted are mesoscale, but they're not fully realistic, they're not fully resolved, and they tend to be a little bit too weak. So why are they too weak? Well, in the real ocean, what is the source of energy for these eddies? There's several processes that give energy to mesoscales. Baroclinic instability is probably the main one. And then what takes the energy back out of mesoscale eddies? Well, there's a bunch of stuff that takes energy out of mesoscale eddies, primarily bottom drag friction, but lots of things. What about in the models? Again, they're primarily driven by baroclinic instability in the models, but they're damped primarily by viscosity. Bottom friction, yes, but also lateral viscosity in the models. So we're not representing the same zoo of processes in the model that exist in the real ocean. So we've got two processes mainly that drive and damp the eddies in the model. The fact that the eddies are too weak, it could be related to the fact that baroclinic instability is not represented correctly. There's not energy coming into them correctly. It can also be related to the fact that viscosity is not representing the loss of energy from these eddies correctly. And that's what we're going to focus on here. So if the viscosity is too strong, then the eddies are too weak. You're taking too much energy out. Why do you need viscosity? Why can't you just lower the viscosity? So if the viscosity is too weak, then the velocity field in your model can start to get a little bit grainy. You can have energy at the grid scale in your model if you lower the viscosity too far. And what's the problem with that? Well, you're using the velocity field to advect tracers, like salt and temperature and other kinds of tracers. And if the velocity field itself is a bit grainy, then when you use it to advect tracers, you can get spurious mixing of the tracers, which can be a bad thing for long simulations, climate applications, things like that. So we want viscosity, but we don't want it to be too strong. Eddies are too weak. That's sort of the setup for this research. So I'm going to develop parameterizations that, yeah. Less spurious mixing, I would say. Yeah, so I'm not at GFDL, but we are using MOM6, so I'll let the GFDL guys make their claims about how much spurious mixing is in the model. If you use the hybrid vertical coordinate system and you use isopycnal below the mix layer, then I do think it significantly reduces the amount of spurious mixing you have, but how much you have and whether you have none is not my argument to make. Well, this is a good question, because there's different ways of getting spurious mixing. You can get spurious mixing associated with vertical advection, which does happen in MOM6, even with the hybrid, with the way that it treats vertical advection. You can also get spurious mixing along your coordinate surfaces. And if your coordinate surfaces are aligned with isopycnals, then you're not going to be having spurious mixing that's diapycnal. It'll be spurious mixing still, but it'll be spurious mixing along the isopycnals, which is spurious, but maybe not so bad. Whereas if you're in a model where the coordinate surfaces are not aligned with isopycnals and you get spurious mixing along the coordinate surfaces, then you will be spuriously mixing across diapycnals, which is really a problem, right? So if you have a z-coordinate model and you have spurious lateral mixing, that's a real problem because you're mixing diapycnally. If you have a hybrid coordinate model and you're getting spurious mixing along coordinate surfaces, it's still a problem, but maybe not as much of a problem. Well, we still want the eddies to have the correct amount of energy, though. We want to have a correct representation of mesoscales, if possible, which is a separate issue from the spurious mixing one. So yes, so this is why we won't have backscatter. I'm delighted to have discussion if people want to interject like this. So I'm going to do a quick review of some viscosity parameterizations for ocean models and general models. Partly of interest, but they give context to what I'm going to do. So I'm starting with Smagorinsky. So Joe Smagorinsky was the director of NOAA's Geophysical Fluid Dynamics Lab for a while. For that, he was a scientist working at the GFDL. And he developed a viscosity parameterization that has been reasonably successful. I like it, but I understand that it's not perfect, and other people have updated it. But Smagorinsky's viscosity is based on Kolmogorov turbulence theory. So you have a range of scales where you have a cascade of energy. And I've written eta here, but you can think this should be epsilon. So you have a cascade of energy going from large scales to small scales through an inertial range. And eventually it gets to a range of scales where it gets removed by viscosity. That range of scales is called the dissipation range. And Kolmogorov theory, just the early Kolmogorov theory, can be used to predict what is this length scale. And so the dimensional analysis says you've got a cascade rate epsilon, you've got a viscous coefficient nu2. The dissipation scale should only depend on those two things. Dimensional analysis then says this is your dissipation scale. It's called the Kolmogorov scale. Smagorinsky then said, what if we increased the viscous coefficient so that the dissipation scale was resolved on the grid of your model? Okay. We would hope that that would be okay, because the idea is you've got large scales, which are the things you care about, and then energy is coming out of those through an inertial range. And the large scales, the idea is that the large scales don't care about the details of dissipation as long as it's happening sort of away from the large scales, then you're okay. So Smagorinsky's idea is true dissipation is happening at very small scales. Let's just bump that thing up so it's happening at resolved scales so we can resolve dissipation in our model. As long as there's a gap between that scale and the scale that we care about, then we should be okay. You could do that. You could say the dissipation scale is proportional to the grid scale. Let me just increase the velocity or the viscosity, excuse me, until that's true. But to do that, you would need to know the cascade rate epsilon. And in the model, you don't necessarily know the cascade rate. So Smagorinsky's idea was to say there is locally a balance between the energy coming down, the cascade rate, and the dissipation rate. So if there wasn't a balance, you would either get a buildup of energy at small scales or energy getting sucked out of the small scales. If these two things balance, then there's an equilibrium, and you can replace the cascade rate epsilon with the dissipation rate. And the dissipation rate is something that you, in principle, know. You can diagnose that in the model. So you plug that into this expression, you set L proportional to the grid scale, and then you solve for the viscous coefficient that does that, and you get the expression at the bottom. And that's Smagorinsky's parameterization. You can do this if you have, instead of a viscous parameterization, a Laplacian or a harmonic viscous parameterization. If you have a biharmonic viscosity, you can do the same analysis and you get this prescription for the coefficient on the biharmonic viscosity. You might want to use biharmonic because it's more scale selective. It preferentially applies at the small scales more than viscosity does. And so you have more of an inertial range where the viscous closure is not active if you use biharmonic. That's one of the motivations for using biharmonic. So this is great, and it has actually been implemented in various ocean models. But when you're thinking about ocean models and the ocean mesoscale in particular, the turbulence theory here doesn't really make sense. So the Kolmogorov theory of turbulence is homogeneous isotropic turbulence. It's not ocean turbulence at the mesoscale. Ocean turbulence at the mesoscale, if you expect a cascade of anything at all, it's not a forward cascade of energy. It's probably a forward cascade of enstrophy, if anything. So Chuck Leith has a paper from 1996 where he repeats this analysis for 2D turbulence. I'm not sure if he was thinking about the ocean or not. I should reread the paper. But it's based on 2D turbulence theory. So in 2D turbulence, you have a forward cascade of entropy. you can redo the sort of Kolmogorov dimensional analysis to find what's the dissipation scale for the entropy cascade. That's this expression at the top. Then you can assume that there is a local balance between the entropy cascade rate and the entropy dissipation rate. Plug that back in, say that I want the dissipation scale to be proportional to the grid scale, solve for the coefficient that achieves that. And this is your Leith viscosity coefficient. It's analogous to Smagorinsky, but for enstrophy instead of energy. Again, you can do that for biharmonic, and you just get slightly different expressions. So these have been advocated for ocean model use by Baylor Fox Kemper, Demetrius Menamenlis, Brody Pearson, Scott Bachman, and others, their collaborators. They've implemented this, they've tested these. They have extended it from 2D turbulence to QG turbulence theory. So instead of an entropy cascade, you have a potential entropy cascade. You get a different closure. They've implemented and compared. I'm not working on these. This is not my research, so I'm not going to spend much time talking about whether it's a good idea or not. They do argue that it has positive effects. My point is that these closures are based on reasoning about the entropy cascade, but the turbulence theory, just the very basic turbulence theory, tells us more about the entropy cascade. The other thing that we usually learn about the entropy cascade in sort of introductory turbulence is that there shouldn't be an exchange of energy through that range of scales. So you've got this range of scales up here at the top with an enstrophy being cascaded towards small scales. Within that range of scales, there shouldn't be much energy going in either direction at all. Whereas these viscous closures, they do remove energy at the small scales, which means you do have energy getting cascaded towards small scales, which is inconsistent with the sort of basic theory of large-scale ocean turbulence. So I want to change things to fix that up. I want to have the entropy cascade being truncated on the range of scales that's resolvable on the grid. But I also want to have as little energy dissipation as possible. And that way we can get, hopefully, appropriate mesoscale eddy energy. How am I going to achieve that? So I'm effectively going to have two constraints, an entropy constraint and an energy constraint. So I need two terms. I can't do this with just one term in my closure. So I'm going to use two terms, combine a Laplacian and a biharmonic. And I'm not the first person to do this. Again, I think in the context of atmosphere and ocean modeling, I think the first person to do this was probably Malte Janssen in 2014 and 2015. Other people have done this kind of thing, but they typically used a stochastic forcing instead of this viscous term. So the idea here is that the biharmonic term is damping. It has a positive coefficient, but the harmonic term, two derivatives, is anti-damping. The coefficient is negative. So that's going to be a backscatter term. Other people had previously used stochastic for that. I'm going to use the one that Malte advocated. So before I tell you how to set the coefficients, I'm actually not going to use that form exactly. I am not using this form that I've just showed you. I'm going to use a slight variation on it, and I want to motivate the variation that I'm using on this form. So going back to the very beginning of the talk, I want to keep my velocity smooth at the grid scale to avoid spurious mixing, which may be diapycnal or isopycnal, depending on how you've configured your model. Either way, it's still spurious. I want to avoid it, so I want to have a smooth velocity, which means I need a dissipation. I need my combined closure, the harmonic and biharmonic terms, to damp scales that are near the grid scale. If I'm pumping energy in at the grid scale, the two combined terms pump energy in, that's bad. There's not going to be anything to smooth. So I want to smooth at the grid scale, and I want, in fact, there to be a range of scales close to the grid that are all damped. And I like the rule of thumb that the top 1/3 of wave numbers on my grid should be damped. Maybe you want it to be 1/6 or 1/5 or 1/10 or 1/3 or whatever. But if you pick some number and you say this range of scales should all be damped, you get a relationship between the allowable values of the backscatter coefficient and the biharmonic coefficient. The backscatter coefficient is negative, but it can't be too negative because then you end up pumping energy into the grid scale, which is bad for the model. I am going to smooth my velocity here. So instead of having a U, I'm going to have a U bar in my closure. And the bar corresponds to a spatial filter. The way I've implemented it in my MOM6 implementation is with a 5-point moving average filter in both directions, X and Y. So 25 points total. And I actually originally implemented this as 2 3x3 smoothers, and then I just condensed it down to 1 5x5. And the way I've constructed that spatial filter is that it zeroes out grid scale noise. So in my closure, I am not putting any energy into the grid scale at all by construction. I'm only putting energy into an intermediate range of scales. What this does is it allows me to have a larger backscatter coefficient while still keeping my velocity smooth. So to briefly illustrate this, I've got here on the left, range of wave numbers, large scales, and then 1 is my grid scale. The blue line is k to the 4th, that's the damping, minus k to the 4th. The red line is k squared. This is sort of the Malta's thing, where it's just negative Laplacian and then damping harmonic. And then the lines in between are combinations of those, and the purple line is an example showing that if your viscosity, your backscatter coefficient is big enough, you can get a situation where you have backscatter on all your result scales. Nothing is damped. That's a problem. On the right, k to the 4th is my damping. The red line here, the blue line is damping. The red line is k squared, but now smoothed. And so it goes back to 0 at the grid scale. And now, no matter what coefficients I use, I will always have a range of scales near the grid scale that are damped. So the purple and the yellow lines are combinations of k to the 4th and the smoothed k squared. And then the furthest right panel is the yellow line and the red line. They both have the top 1/3 range of wave numbers damped. So from here to the end, damped. The yellow line uses the unsmoothed backscatter term, and the red line uses the smoothed backscatter term. And you can see that with the smoothing, the red line, I'm getting more damping at the grid scale. So I'm going to have smoother velocities, but I am also getting more backscatter. So this smoothing on the U bar there, it helps me get more backscatter. It helps me keep a smoother velocity on the grid.
Well, there's not much backscatter, right? In any case.
Yeah, this
very shallow.
It is a backscatter coefficient, I guess. Yeah, it's not a huge coefficient. If you wanted more, you could do more smoothing, but it's not huge.
One more question.
Yeah.
So your smoothing is equivalent to identity plus some coefficient multiplied with Laplacian operator. Right? So what you're doing can be also reformulated and just adjusting amplitudes of Laplacian and biharmonic operator.
It's not a question, Zagi.
Yeah, so the whole thing.
It seems to me that it can be done, yeah.
Yes, so in Fourier space, this is just a quartic polynomial, which means you can do it with a combination of a constant, a Laplacian, and a biharmonic. But at the level of implementation, I do it using this spatial filter, yeah. And I believe that Stefan Jurka has done a sort of similar use of filters So instead of doing, well, anyway, he's used filters to achieve similar kinds of effects. Yeah, sorry, he's the lead author, so.
But it's still a bit disappointing, right? Is there no way to increase this red line on the positive range of the red line?
So given that I want to have my top third of wave numbers be damped, and then given that I'm only doing the smoothing the way I'm doing it, this is the most you can have.
Or can you use higher order operators to make it more?
Yeah, so if you use higher order operators, or if you do your smoothing differently, effectively you're going to polynomials of higher order in K, you could get this higher. Or if you allow the range of wave numbers to be a little bit smaller, you can get this to be higher as well.
And it can be a dispersion because the spectrum, energy spectrum is C. So it is proportional to energy spectrum, right? So it's spectrum. So it might be contributing quite a lot.
Okay, because there's more energy.
Yeah, because of that.
But plotted this way, it's not so convincing.
Right, so that's a good point. And just to say it again, this is effectively a coefficient. This is not the actual backscatter rate. It's not a rate at which energy is coming in. To get the rate at which energy is coming in, you have to multiply this coefficient by the energy that's already present in that range of scales. And typically we have a downward sloping energy spectrum. And so you get the damping here is multiplied by something that's quite small. And at this intermediate range of scales, the backscatter is multiplied by something that's much bigger. So you can achieve, in terms of energy per time, you can achieve a pretty good backscatter with this thing, even though the coefficient is maybe not very big on this plot. We've said that now 2 or 3 times, so thank you, but I'll move on. Okay, so now I'm going to do 2 constraints, two unknowns, and find nu2 and nu4. So there's a little bit of interest here. First, I want my dissipation scale for enstrophy to be resolved on the grid. And I've got to go and figure out, well, what's the appropriate constraint? So here we had dimensional analysis, enstrophy cascade rate, dissipation scale for enstrophy. And there was only one coefficient in that dimensional analysis. But now I've got 2 coefficients, a backscatter coefficient and a damping coefficient. And I've got a cascade rate. If I do the dimensional analysis, I won't get I won't get one number anymore. There'll be a combination of different things. So my argument here is I have zeroed out the backscatter at the smallest scale. So the dissipation scale for the entropy cascade, it should only depend on the biharmonic term, which is the damping term. It shouldn't depend on the backscatter term at all. So I'm still going to use this expression for the dissipation scale, and I'm going to set the dissipation scale proportional to the grid scale. If I also used this expression for the cascade rate, I would just get back the same biharmonic Leith scaling for the viscous, the biharmonic coefficient. But I'm not going to do that. I'm instead going to have the enstrophy cascade rate balanced by combination of the backscatter term and the damping term. And the idea here is you've got large scales, entropy, coming in. And then at the small scales, you've got the combination of the backscatter and the damping. And the backscatter is backscattering energy, that's the point, but it's also backscattering entropy. And so I want to assume that there is a balance, a local balance between the entropy that's coming in from large scales and the combination of damping and backscatter of entropy from my closure. Yes?
If you apply the filter, this means that you already remove something like the high order wave numbers for the first term. That's why you have only the second component for the
Yes.
So you can apply the same formula for U4.
Yes. That's right. So my argument for using this expression at the top, right, is that I've filtered out so the new 2 term doesn't operate in the dissipation range anyways.
To set for the eta, it is operating.
Right. And so
Cheating, right?
it does seem a bit like cheating. Let me try to respond to that. So if you look here, the peak backscatter rate is about halfway. It's about halfway through the range of scales, which on a linear scale, it looks like, well, that's not a small scale. But if you go to how we're used to looking at spectra on a log plot, you know, this is maybe 1/3 and 1/2 is like here. Okay. Let me do it online so people can see. So your dissipation range is maybe 1/3 of wave numbers, and your backscatter is going to peak like right here, which is a factor of 2. That's still what we would think of from an energy spectrum perspective as being pretty small scale. And the large scales are actually way out here. So my argument is, yeah, the dissipation scale depends only on the new 4 coefficient, but the cascade rate is coming from really large scales. And what it's seeing down here is the combination of both the backscatter and the dissipation. So then I have this expression for the dissipation scale, and I have...
If you would also put the new 2 in the L equation, can still solve it, right? Or not?
Yeah, but then it's, you get a sort of an unknown function. Because when you do the dimensional analysis here, if you have nu 2, it doesn't just reduce to a constant times this expression. It becomes a dimensionless constant times an unknown function of some dimensionless parameter group. And we don't know what that function is. So I would have to do more work in that case, which you could do and maybe you should do, but I've taken the simpler route here. Or maybe I should say I could do and maybe I should have done, but I opted to take the simpler route. So that's how I'm going to deal with the enstrophy constraint. I have not written down the equation that results from that, but you get one equation with the 2 unknown from that. Then the next constraint, I could say, okay, on the left, I've got the kinetic energy backscatter rate associated with the backscatter term. And on the right, I've got the kinetic energy dissipation rate associated with the biharmonic term. And if I set those 2 things equal to each other, I would say the backscatter is backscattering at the same rate that the damping term is damping. So the combination is no energy dissipation. I have instead opted to put a little coefficient CK in there. So if CK is 1, then no net kinetic energy dissipation. If CK is 0, then that means I'm not going to backscatter at all. I'm just going to have the dissipation is going to do whatever it wants to do. Okay. If CK is 0.5, I'm going to backscatter half of the rate at which biharmonic is removing energy. So it allows me a little bit of extra flexibility there. Typically, we just use CK equals 1 in our simulations, but I'm allowing for the flexibility. Okay, so then you get 2 equations, 2 unknowns. It's a nonlinear system, but it ends up just being quadratic, so you can solve it. And this is what you get. So I've got the backscatter coefficient is negative, and it's proportional to the biharmonic damping coefficient, and the proportionality constant I'm calling m up to a minus sign. That depends on CK, which is the fraction of the energy dissipation that you want to backscatter. Once you know CK, well, the damping rate, the biharmonic term here, if m was 0, so if the backscatter rate here was 0, you would actually just recover the standard biharmonic Leith scaling. And if the backscatter rate is not 0, maybe counterintuitively, the biharmonic term actually gets smaller. Okay, so the biharmonic term when the backscatter starts to come up, the biharmonic term actually starts to go down. You can't really use this directly in a model for several reasons. One of which is that the solution doesn't always exist. So this thing, there's a square root here, and this thing inside the square root is not necessarily positive. So it doesn't even necessarily always exist. And then even when it does exist, practically speaking, this doesn't guarantee that I'm getting the nice dissipation range that I want. At small scales, 1/3 of my wave numbers, I want them to be dissipated. This doesn't guarantee that. So I make some modifications for practical implementation. The first thing I do is I specify a minimum value for the biharmonic coefficient, which is pretty common in ocean models. You don't want your biharmonic coefficient to go to 0. So there's a minimum value. And then I compute first the biharmonic Leith coefficient without any backscatter, just the standard one, and I compare it to the minimum value. And if it's below the minimum value, I of course still use the minimum value. But then if it's below the minimum value, I just say, we're not going to backscatter here. There's nothing going on here. There's no enstrophy cascade. The dissipation is really weak. You know, I'm not even rising above my threshold of the background. I'm just going to turn backscatter off. Then I go ahead and actually compute this. And then I say, all right, the backscatter coefficient that it wants, is it too big? Is it so big that I'm not going to have enough dissipation on the grid? And if it's predicting a backscatter coefficient that's too big, then I bring it back down to so that I get a 1/3 dissipation range. Effectively, what that does is it brings the M coefficient down. Then, if you just compute that and you visualize it for a snapshot, it's really grainy. So you get very large and very small values next to each other, which is not great for numerics, and it's not great for performance of this. This is a common thing in even the QG Leith. It's not a property of backscatter. This is just when you do nonlinear viscosities, they often tend to be pretty grainy. So I'm going to smooth it, but I don't just smooth it in the normal way, because you might have, in some place it's saying, oh, you really want a large viscosity here to truncate the enstrophy cascade range. And then you smooth it and it comes down, and now you're not truncating the cascade anymore, not on the grid scale. So what I do is I square it first, then smooth it, then take the square root. And what that does is, rather than bring the large values and the small values down to some intermediate, it leaves the large values pretty high, and the nearby small values then come up. So I'm making it a little bit more viscous than it would be if I was just doing a pure smoothing. I also smooth the M coefficient there that creates the backscatter coefficient from the biharmonic coefficient. So practically speaking, that's how I implement this. So I presented this in a QG context. I implemented it in a QG model, this and many other variations, and compared them, and it worked pretty well. I was in between postdocs at the time. One postdoc had just left. The other one hadn't hired yet. So it's a single author paper. But then just after this came out, I got a new postdoc to work on this, Hussam Yassin, and I implemented this in the MOM6 ocean model 2023, and then Hussam took over evaluating this in the quarter degree ocean model, which I think is more of interest to people here than the QG. So after 2 years, we have a paper here in review at Journal of Advances in Modeling Earth Systems. It's past one round. We're in revisions now. The preprint is online. I'm also happy to send you the preprint if you send me an email. But just a quick summary here is that when you turn on backscatter in our quarter degree ocean model, but I think also in other people's models, not just this backscatter that I've implemented, but other backscatter schemes, typically what happens is you get increased transport of heat towards the Southern Ocean. Seems to be fairly generic across backscatter schemes. And if your ocean model has initially a cold Southern Ocean, then this is great because it removes a bias or it decreases a bias. But if your ocean model already has a warm Southern Ocean, this is a problem. And that's where we were. Our MOM6 ocean model configuration at 1/4 degree had kind of a warm Southern Ocean to begin with, and you turn on the backscatter and it makes it warmer and starts to melt sea ice, and it's a problem. So we did a bunch of stuff to sort of patch this up. We did some combinations of GM in one location and backscatter in a different location, and we got something that was the best we can do in terms of increasing the kinetic energy in the model is a 25% increase. We can increase it more than that. We could do a 100% increase if we wanted, but then it would melt all the sea ice and be unrealistic. So the best we can do while maintaining some degree of realism is a 25% increase, which is good, but you know, it would be nice if it had been more and better. And instead of going deeply into these results, I think here the conclusion is just that 1/4 degree is hard. So last time I was in Hamburg was for the Commodore conference in 2020, 6 years ago. And I remember distinctly Julie Desai was there, and she was talking about how hard 1/4 degree modeling was. Their group had been an early adopter of 1/4 degree modeling with NEMO and had been doing it for a while. By 2020, and she came there and said she wasn't sure if she was worth it. Because you generate a lot more carbon with these simulations than you do with the low-res model, and it's hard to do a good job with 1/4 degree. And at the time I thought, but you know, she doesn't have backscatter. We have all these ideas for how we can improve things. And now I'm older and wiser. And yeah, 1/4 degree is just hard. So this is not a silver bullet. It does help things, but 1/4 degree is hard. But this story has a bit of a coda. So I'm involved in developing the workhorse resolution, the non-eddying resolution at 2/3 of a degree configuration of the ocean model for CESM. And a year ago, January 25, we thought that just the biharmonic Leith closure without backscatter would maybe help with the equatorial undercurrent in our model. And so we ran a simulation where we turned on my backscatter scheme, but just with the backscatter coefficient set to 0. Because it's an implement, when you do that, it's just Leith biharmonic. So we set CK to 0, we wanted to, and then that gives you an implementation with no backscatter. But my colleague who set this up, Gustavo Marquez at NCAR, he accidentally left the backscatter turned on. So we say in climate modeling, there are no accidents, only unintended experiments. And so this was an unintended experiment, and it had surprising results. So before I tell you the results, a little bit of background. I said practically this scheme only turns on if you go above the background. So we have a background of 10 to the 12th meters to the 4th per second in this model. And this only turns on at the equator, but why does it only turn on near the equator? So I need to go a little further back. Let me go all the way back to biharmonic Leith here. So this is the biharmonic Leith, and you can see it depends on the grid size to the 6th power. And we're just using a Mercator type grid. So the grid is biggest in the tropics at the equator. And as you move towards high latitudes, the grid gets smaller. And then you raise that to the 6th power. And this biharmonic coefficient has a very strong dependence on latitude. It's biggest near the equator, and it drops rapidly away from that. And backscatter only turns on when this thing is above the background. And this thing in this model happens to be above the background near the equator, but below the background when you get outside the tropics. Okay. So this has an effect in the tropics in this model, and this is one of the effects that it has. So this is a meridional section through the Pacific Ocean at the dateline, showing the zonal velocity. And the top is our model without backscatter. The big red blob here is the equatorial undercurrent, which is a real feature. Basically, everything up near the surface is real features, that are resolved to some degree in the model. Below that, you get some zonal flows, but they're unrealistic. And when you turn on backscatter, the surface stuff stays qualitatively the same, but below that, below the thermocline, it changes the zonal flows significantly. In particular, you get these two lobes of eastward flow at about 300 to 400 meters depth. That's the core, just off the equator, plus or minus 3 degrees. These are actually real physical features that are now appearing in the model with backscatter. They have several names in the literature. I like the name Tsuchiya jets. That's a Japanese researcher who was one of the first to discover these jets. Then below the equatorial undercurrent, you have a countercurrent, which is also a real physical feature. And then below that, the direction of zonal flow oscillates. So these are the stacked jets that have been discussed in the literature for zonal flow at the equator. So we're significantly improving the flow there subthermocline in the equatorial Pacific.
The new stuff realistic? Is it not an observation?
Yes.
Current?
Yeah. So these things are seen in observations.
Yes, but the intermediate current below the undercurrent, is that really?
This one here? Yes. So you do see a reversal of the flow below the equatorial undercurrent.
But there was a big debate a couple of years ago, right? If there's really a mean flow like that.
Okay.
There wasn't in the end.
The OBS product that I've been looking at has this, but there may be more to the story. I'll just leave it at that the OBS product that I've been looking at does have that.
Kind of ops product, is it?
It's Johnson 2002. I can't say much more. It's just part of our standard diagnostics package. Yeah, maybe I'll look it up and tell you afterwards. The Tsuchiya jets are definitely there as well.
Yeah, they're known.
What does the parameterization do to make this difference? Physically. What kind of physics changes? And
X-moities.
So these jets, they sort of start off of Indonesia maritime continent on the, from your perspective, western side of the Pacific. And then they come off, and in the low-res model, you can see them kind of incipient. They're starting out, but they just don't extend. And with the backscatter, they do extend further out eastwards across the tropical Pacific. And I think it is as simple as just that without the backscatter, they just get dissipated by the viscous scheme in the model. So they're there like they should be, and they're getting started, but they get wiped out, smeared out. And by putting in this backscatter, we are countering the effect of that smearing viscosity so that they can maintain themselves further out into the Pacific Ocean.
those currents are directly forced by the parameterization time.
Yeah. When you look at the backscatter coefficient, it's spatially variable. It's right on these. It shows up right on these currents. In between them, it goes lower.
So Chia jets are also eddy driven or wave driven at tropics?
Well, actually, there's debate in the literature about what drives these things in the real ocean, and there's multiple mechanisms that have been proposed, and so I can't speak directly to that.
But all the waves play a role. You have more waves or more eddies by this backscatter.
Do we have more waves by the backscatter? So
more eddies. That's your
more eddies
idea.
Well,
as this
yes,
limited dissipation, just limited.
It's obvious more eddies, more eddies.
More eddy variability. You don't see a whole lot of coherent mesoscale eddies per se, right, in the tropics, but
they're waves, right? They look like waves, not eddies anymore.
Right. So you do see more of that variability. We have not looked at diagnostics of, say, Kelvin and Rossby waves in the ocean, in the Pacific, in these runs. But if you just look at a movie, you do see a lot more variability.
Tropical instability waves.
Tropical instability waves are definitely affected by this. And some people argue that the Tsuchiya jets are related to the tropical instability waves, and some people argue that it's not related at all. So I don't have an opinion in that debate.
Oh, but here we have the proof, right? You have more tropical waves and more Tsuchiya jets. So that's the proof.
That may be the explanation, yeah. The tropical instability waves are there in the model without. And this gets back to something I thought I would mention is the motivation for this and the underlying theory. You might think it breaks down at the equator because there's no geostrophy at the equator. But really, you don't need geostrophy per se. All you just need is approximately 2D dynamics, which you can motivate from just the anisotropy, strong stratification, thin fluid. So even at the equator, sort of 2D turbulence type ideas can still apply at the larger scales. So the theory behind this can still make sense. You do have strong beta though. And so we're pumping in some energy to the eddies, but then beta is having a big effect, which may or may not be related to the formation of these jets. I can't say for sure. But moving on, these jets are interesting, but from a sort of climate model perspective, you might say, so what? Does it have any effect on climate? And we're not really sure. But one of my colleagues at NCAR looked at this and he said, so he does ocean biogeochemistry, and he said, in these low resolution models, we have a big problem with the oxygen minimum zone in the Eastern tropical Pacific. So in the real world, there is an oxygen minimum zone in the Eastern Pacific. And in the models, it's too big. So the oxygen minimum zone at 400 or 500 meters deep is too big in the models. It's not getting ventilated enough is the problem. There's not enough fresh oxygenated water coming into that region in the model. And he looked at these plots and said, hey, that might help with the oxygen minimum zone bias. And so we ran some runs with BGC turned on, and indeed it does. It improves, you get oxygenated water from the Western tropical Pacific coming in these jets and ventilating the Western tropical, sorry, I keep flipping that. It comes from the West, it goes to the East. And it improves the oxygen minimum zone. And because of that, we have decided to actually use this in the forthcoming CESM3. So it will be turned on by default, even in the non-eddying configuration of CESM3.
Well, it's non-eddying anywhere else, but in the tropics, it's
right. It is eddying in the tropics. Thank you. That's a good point. Yeah, because the deformation radius gets much bigger in the tropics. And so it is eddying in the tropics, which is also where this turns on. We've also noticed after the fact in fully coupled runs that it improves Nino 3.4 variance. It shortens the autocorrelation of Nino 3.4 index, and it improves the transition to La Nina. So it is having some coupled effects as well. And they are salutary effects, so we're leaving this turned on.
You switch it off anywhere else?
The only switching, yes. So getting a bit into the weeds here, but we found that, and we're unsure why, but this leads to some problems at depth. Doesn't do this in the quarter degree runs that Hussam did, that I talked about here. But in the low res model, we have some spurious circulations at depth, and I mean like 2-3 kilometers deep. So we are going to, I added something that turns this off. It scales the backscatter out, starting 1 kilometer deep down to 1.5. So at above 1 kilometer's depth, it's just doing whatever it does. And then it starts to scale down. And by the time you get to 1.5 kilometers, it's 0. And below that, it's off. And we did that. It's ad hoc. I don't have a theory for that, and we only have to do it in the low res model, not the quarter degree model. But that's the only other place where we're selectively turning it off.
Well, you also turn it off in the mid latitudes.
Right, but it does that by itself. It doesn't rise above the background, so it just turns itself off.
Sorry for the interruption. I think we should keep the discussion for after the talk so we can listen to what Jan has to say.
Yeah, how much time do I have left?
Not enough. You can just go ahead and finish your talk.
Just go ahead and finish? Yeah. Okay, let me go. I'm going to.
No, I mean, the way you want it to go.
Well, I don't want to.
But we can stop the interruption in between. Then we can do the question session later.
Okay. I want to respect people's time. Do I have 10?
I think we have enough time. So
Okay.
Go ahead.
Okay.
I just have to excuse myself in advance for the teaching, so I'll be leaving in a couple of minutes.
I fully respect that. Thank you for letting me know. And sorry for going long. Okay, so new kind of backscatter. The title of my talk is To Backscatter. That was just one of them. So I also have a scheme that is designed for non-eddying resolution models. The previous one was designed for eddying, but we're using it in the low res. Here, this is designed for low res. So even non-eddying models are deficient in variability. So if you just look at like SST at a point, the real ocean is going to have variability, and a lot of that variability is going to come from mesoscale eddies. And then if you look at a model whose resolution is so coarse that it just can't resolve, it can't represent mesoscale eddies at all, that model will be missing that variability, and there's nothing you can do about it, right? Because it's below the grid scale. But also, that model is typically missing variability on the scales that it can resolve. And that variability dynamically can come from lots of processes, but one of the things that can drive variability on those scales is mesoscales. So the mesoscales themselves are variable, and you can't get that in a model that can't resolve eddies. But the mesoscales also drive variability on the larger scales, and that's something that you should have and is frequently missing. So that's what we want to address with this backscatter scheme. There is some prior work on that. So this is a paper by Scott Bachman, formerly at NCAR. The question here with this type of thing is, how do you set the backscatter rate? So previously we knew we're damping too much energy with viscosity, so let's fix that. In a low-res model, you don't have eddies. You're not damping the eddies too much. So you don't have that same background to set the backscatter rate. So how are you going to set the backscatter rate in a model that doesn't have eddies? So we need a different theory. And I'm going to rely on this parameterization by Scott. So in a low-res model, you've got Gent-McWilliams parameterization. And what Gent-McWilliams does a bunch of things. Energetically, it removes potential energy. So you've got wind stress blowing over the ocean, tilts the isopignals, generates potential energy, and then GM slumps the isopignals and takes the potential energy back out. In the real ocean, that energy that's coming out of potential is just getting converted to kinetic through baroclinic stability, and the kinetic energy cascades back to larger scales where it can be dissipated by drag or by other processes. GM in the model, it just takes the energy out and then it's done. It doesn't get back into the resolved scales. So Scott had a parameterization in 2019 where he did a backscatter where the rate of backscatter is proportional to the rate at which GM is removing potential energy. So it just pipes it right back into the kinetic energy budget of the model. Malte Janssen and collaborators also had a paper at about the same time where they said, we're going to take the energy that GM removes, we'll put it into a subgrid scale energy budget, and then we'll have the backscatter rate be proportional to the subgrid scale energy, which is a related idea, but not exactly the same. For the sake of time, I'm going to skip this. Basically, we're going to do this with stochastic backscatter instead of using a negative viscosity coefficient. And this was done with Niraj Agarwal, who was a postdoc with me, and Phil Pejon, who is a scientist at NOAA's Physical Sciences Lab. They're not part of the CPT, so their names weren't at the beginning, so I wanted to specifically mention them. Phil Pejon in particular was instrumental in the implementation here. He ported a random pattern generator from the atmospheric model and piped it into MOM6 so we could use it. And I couldn't have done this without that. So you can think of what we're doing as adding a stochastic forcing in the momentum equation, and that stochastic forcing could model eddy stress divergences. Practically speaking, though, what we do is the model takes a time step, and then we stop the model and add an increment to the velocity, the lateral velocity field, and then the model takes another time step. That's how we implement it. So these increments, we have to construct them. What do they look like? So their amplitude of these velocity increments is set so that the kinetic energy backscatter rate is proportional to the GM work rate, the rate at which GM is removing potential energy. Their horizontal structure, so we're only incrementing the lateral velocity, and our increments are incompressible laterally, so we're not driving vertical flows. Caveat is that right next to land boundaries, we do have a little compressibility, but away from that, we are exactly incompressible. We use this random pattern generator that I mentioned earlier. It's based on spherical harmonics that we interpolate to the model grid. And you can use an arbitrary spectrum. We use a spectrum that is Gaussian for the stream function, so it drops off, it's large at large scales, drops off. And then the stream function, we take the derivative of that to create the velocity increments. The vertical structure is proportional to the first surface mode. So it's not barotropic, it's not depth independent. If it was depth independent, we would be adding velocity near the bottom, which is not always realistic and which could cause topographically generated waves and stuff. So we don't want to increment the bottom velocity. The vertical structure that we use is this surface mode. Practically speaking, that's just what's available in the model, so we used it. But it does seem to work well. And then the time structure, we don't use white noise in time, but we do use fast noise. So it's an AR1 because that's easy to implement. So exponential decay of correlations. And we have a 6-hour decorrelation time, and 6 hours doesn't matter so much. We just want it to be fast. And why do we want the decorrelation to be fast in time? It's so that we can accurately control the kinetic energy backscatter rate. So if the noise itself has long correlations in time, then the rate at which the energy is coming into the system depends on the correlations between the velocity that's already there and the increment that you're adding. If the increment is very fast in time, then the correlation between the increment and the velocity that's already there is small, and that makes it easy to control the backscatter rate. So that's why we do fast noise. Okay. So here's a video of SST in the Southern Ocean. This is all based on GM, and GM is strongest in the Southern Ocean, so you see the biggest impact in the Southern Ocean. And the top one doesn't have the backscatter, and the bottom one does. And I think the way to look at this is to pick a region and just look at that. So maybe just look at below the Agulhas, or the Agulhas retroflexion. Maybe just look at that. And hopefully you'll see that I've got more variability both in time and space in the bottom one, which is the backscatter. Now, if you look at the South Atlantic, similar, if you pick some region in the ACC and look at that, again, a little more variability is visible. This is the speed at the surface. And again, if you pick a region like the South Atlantic and just focus on that, you can see there's a little more variability. I just made these videos myself, and I'm not great at making videos. I acknowledge that, but it's something. Okay, it does affect the variability. So SST variability, for example, this is an OBS product, OI-SST v2. This is the difference between the control run without backscatter and the OBS product. Blue means we're deficient in variability, so we're blue over lots of the ocean. And then this is 3 stochastic runs. It's the difference compared to the control. So we want the color to be opposite so that we're reducing biases. The 3 rows are different length scales for the stochastic increments. Top is small scale, bottom is large scale. Generally, you do see red, so we are reducing generally biases. Going through this quickly. This is marine heat waves. I used the Python package for marine heat waves. This is the number of events per year. And this is Bob's product. This is CESM2. And there's just not as many marine heat waves in a low-res model in CESM2. This is CESM3, but without the backscatter. And thankfully, in CESM3, we do have more marine heat waves. It's a little more realistic. And then with the backscatter is up here. So we increase it maybe even a little bit too much, although I will note this is a qualitative color bar. So we are increasing it a little bit too much, but maybe not a lot too much. We also find in the coupled runs that this stochastic version of GM+E reduces southern hemisphere sea ice. It is, again, just like in the quarter degree model, it's pumping more heat towards the Southern Ocean. But that's good in this model because our ocean is a bit too cold and we have too much ice. And so this parameterization counters that bias. It brings the ice back to a reasonable level, which is a good thing. So we're going to have this turned on by default in CESM3. And special thanks to the NCAR Ocean section. I didn't mention them. Again, I wouldn't have been able to do this without them. And thank you for the invitation and for your patience with this very long talk.